I'm just willing to start with directed overcurrent protection.
Overcurrent protection.
I'm just trying to find myself and my blackboard and something to draw with. Nope. No one coming. Where I'm willing to start? Yeah, I'm willing to. Let's say we have a simple distribution. We have a simple distribution network. And here, for example, another customer. It's a distribution network, I don't know, 3, 10, 20, name it, kilo. Distribution network, isolated neutral, everything simple. Until one nice day, this customer decided to go up and install wind turbine, solar system. So we have what here? Second source. Maybe with some local load, it's not important. Important what we see a second source. If they are big enough, we'll need to do what? We will need to install switch and protection. Why? Because in case of fault, we will have two currents. We have a double fed network. Double fed networks are known for a long time. It's not something new, because you know what happened? First, they are more reliable. Very well known design is a ring type network where you can power each segment from two sides. This means that in case of repair work, you don't need to disconnect any customer. Here's feeding transformer. Ring type networks. Networks like at some moment your customer base grows. At some moment existing network is not capable to power all these customers. And starts what? Let's take power from another end. We have substation in vicinity. So let's power network from the second side. Here in Riga, we have some segments where factories were built. And for factory, one is not enough. Another thing, large clients like shopping malls, they need two independent sources. Because they need reliable power for fire extinguishing and smoke escape, so on. At some moment they start pushing distribution network, can you bring us another source? And at the moment we start to think about the two-side fed network. Okay, here is my two-side power network. It can be or link between two substations, simpler, or I have a generator on the one of the sides. It's nothing unusual today. People funding and build nice solar power plant. Oh yeah, and we are here. We have double fed network. So if we start to analyze, I'll need to draw this simple law. It's a chart. It's a current as a function, fault current as a function of fault distance. For I1, it will be something like this. Square of 2 divided by... It's a solid line, three-phase fault, dotted line, face-to-face, two-phase fault. Distance between them approximately 0.866. Fine, but I need to draw a second line. The second line here is for I1, this one for the I2 for current from the other side. And it will be something like this. Something like this. Maybe I use that. Come on, yellow. Bit of yellow, and this one will be red. Who's calling and why? I will kill them. missed timing, and now he wants to study our program, but okay, it's not important. It will be, it's solvable. Where am I? I have drawn two currents. Now let's see what we have with our relays. This will be A, B, C, and D relay. Where to draw a fault? Maybe here. Here is my fault. It should be cleared with this switch. So, here, approximately here is possible fault current, and trip current for the switch should be here should be at last 20%. So this relay should be sensitive. In reality, I need to take this point a bit lower. Relay should be sensitive to minimal internal fault, and it's this one. It should be somewhere here. So here, this point is for 20%. Okay, what do we see? So the blue line is a trip current. Trip current for the C relay. My relay is sensitive. We can compare. So fault current is above trip current. So my relay will be sensitive. It will be sent. In case of this fault, signal will be sent and fault cleared. Oh, look who's sleeping well. We got the distribution network powered from both sides here. And this nice relay, I draw here is the trip current, and here is my current of my fault, and you can see what if fault is above trip current, so relay will send a disconnection signal to the switch and fault will be cleared. Very nice. Now there is one tiny problem. You know what problem? Let's take a look on this relay, on B. What should be a trip current for it? Actually, minimal internal. So, the bottom of the yellow current from the opposite side. Brown. I have brown current. So, here is min internal for B, and it's something like this one. So this nice brown line is a trip current for the B. What the B relay will do in case of this fault? Red current, red current, red current. Oh yeah, red current is well you see this? Red current is above a trip line. So B will operate. You see? B will operate and kill this customer. It's not good. only this switch should operate. This customer should remain. This is not good. What can I do? I can try to set a time. I can create a selective machine with the time. I can do what? I can set trip time here. Let's say 1/2 of the second, and for B, trip time will be 1 second. Selective. At the first look, what will happen? Both will start, yeah? But this one will operate in 1/2 second, will clear fault, and B will return. Fine? Fine. This was fault 1, and I'm drawing the fault 2. What will happen in case of fault 2? 1 current. This is current for this one. We need to look on this one. It's a current that will flow through C and D. You can see both will start, and since here I have shorter time set, C will trip first. Again, killing this customer, unlucky. Here we will see extremely angry and unlucky customer. Nothing works. It's impossible to obtain good operation within good management practice without disconnecting customers. Neither with current, neither with time delay. Time delay do not work. Because if there would be a huge difference in currents, again, nothing happens. Again, you will see false trips on the fault behind. See the problem. For example, for these relays, C relay cannot discriminate between direct fault in line, and or fault behind the back, or reverse directed fault. We need to do something. And what can be done? Idea of directed overcurrent relaying. One moment. Draw something like I have source. I would like to put length, let's say, a wattmeter here. More wattmeters. Another wattmeter. Power. Here will be my second source. A, B, C, and D. Yeah, 4 wattmeters. Node polarity. I have planted my wattmeters for please, wattmeter, don't look at me. current, I have terminals for voltage, and there always an in. Assuming what power is positive if current flows in, if voltage is in. What will I get? So, I will do a nice table. Let's take fault number 1. Fault 1. Wait. Here will be fault 1. Fault 1. For fault 1, current 1, and current 2. What about A? Current flows into marked terminal. So, here I will see something positive. Yeah? And for B, current flows, see, green current flows for us. What about C? Green current outflows. This means what it will show? Minus. And here in falls plus. Okay, let's take second flow in orange. In falls plus, and here out flows minus. Inflows plus, inflows plus. So here you see the answer. If I equip my relay with power flow or power direction function, it appears that it can solve my problem. Within discriminate operation on two-side power to line. Yeah? Old, nice power meter. I think this one manufactured before the war. Old, nice meter for distribution for networks which isolate neutral. Actually, this one no, it's not for 100 volts. It's for this one is more close to the customer network. But this one 100%. This one will do 100 volts and 5 amps. First idea what you can do and what being done is to take simple old method, remove all these digit mechanisms and substitute it with contact system. If it rotates forward, it allows operation. If backward, inhibits. So simple relaying function, power active greater than 0. First solution look exactly like this. But is it a good solution? Disappears here. Is it a good solution or not? Disappear. Get the book here. Everything disappears. So, how good is this solution? We need to perform a small analysis. How good is solution based on a simple power method? Simple idea. Piece of line, fold. What can be characteristic of fault loop? I can assume, okay, I will draw, let's say this is voltage of fault. I will use an extremely simple substitution schematic. A and fault resistance. So let's say this is our A. How characteristic of relay power greater than 0 will look on this plane. It's a complex plane. I've assumed a real voltage. For example, ZF is pure active. More simple. Power is voltage by conjugated current. When power is positive, if current, this point, pure 90 degrees away, pure coil, here is a merging point where power is 0, yeah? This point, pure capacitance, here power is 0, yeah? All this area where power will be positive, yeah? So here is the merging line. P greater than 0 and P is negative. Power is negative, active power. Do you believe what matter will rotate in opposite direction? I swear it will. This one rotates and this one rotates in opposite direction. So here is emergence, positive power, negative power. Now, this is merging line for the function t greater than 0. Active power, positive. What is the possible area of fault currents. Fault resistance may be absolute reactive, pure reactance. That means what it will be here. This is when R fault is 0. Or maybe, let's say it's short, it's cable line without inductance. This when X fault is 0. Since possible, all these are possible faults. How good is this method characteristic? Not very. You see what here we are in area where we have no safety margin. Here we are not safe. What can we do? First idea, let's take not the active power meter, but meter of reactive power. Let's assume something like this. This will give us characteristic like this. For the active power, I will mark with plus operation. Operation allowed in this area. For if we take a Varme meter, another meter of reactive power, it will produce as characteristic this way. Also, in this area, not the best one. Actually, we need special kind of characteristic. Standard meter isn't the best one. We need something special. And here starts what? We start thinking about reliability. And for reliability, three-phase fault is possible, but it's rare. Usually, we will start from phase to phase. I'm not talking about ground faults here. It's a distribution network with isolated neutral. Ground fault is a different story. I will speak about ground faults. I need something special here. What's special? What can I do? I'm talking on distribution network. And this time distribution network had a transformer system metering, two system metering, A, B, C, ground point, something like this. I on my disposal is actually triangle voltages. Anyway, voltage to ground isn't the best idea. Good, I'm thinking about reliability. It is preferable to have a voltage system crafted in this way. What in case of fault, for example, I have AB fault. It is preferable to have a C phase voltage you somehow incorporate. So healthy phase voltage. This makes all this design more reliable. If I use unhealthy phase, you see, it's more reliable. Because in case of, for example, I have A phase relay, fault AB, voltage to to 0, I have problem to operate. A, B, C. That's a transformer system. I need to do something to ensure my system is reliable. And what was selected? That 3 different standards, but here in our country it's most popular in Europe, so-called 90-degree system was chosen. Idea why 90 degrees, what is it? I have, let's say, A phase current, B phase current and C phase current. For my function angle between as a polarizing value, AB voltage was chosen. That's why 90 degrees. It's so-called 90 degrees schematics. So signal pair for my direction relay will be UAB and A phase current. For B phase, it will be this which one? It will be for B, AC, and for C, this one. One second, I will draw a comparison table. But for this case, I have A phase current, AB voltage, 90 degrees. It's the YB phase. It's possible that it will remain held in case of fault. I will have voltage on my selection function. Now, if I do like this, what kind of characteristic will I need? Let's say this is A phase EMF. Yeah? This is polarizing. It's polarizing voltage BC. Possible currents in case fault loop resistance is pure active. This will be a fault in case of pure resistance. Somewhere here will be a fault in case fault loop is fully inductive. It's a pure inductive. It's a case F fault is 0, it's a case N fault is 0. So all possible currents will be somewhere here. Meaning what my characteristic, I can draw line like this. But what do I need to check? Huh? Direct faults. All these faults go here. Yeah? So all faults I'm looking on this relay here. For all internal fault, I will deal with current I1, yeah? And all this fault will be in this area. What I need to check? I need to check reverse faults. For these faults, I will deal with current I2. In case reverse direction fault, pure active, what will I see? angle 0 but with minus sign, because current inflows, meaning what it will be somewhere here. In case edge fault is 0, it will go in opposition to A phase EMF. In case air fault is 0, again I will see 90 degrees lag but with minus sign. This is air fault is 0. So all these faults, they will be in this area. All possible. Reverse faults. So what are things? White area, operation allowed. Red area, this brick color area, operation should be prohibited. Yeah? Appears what this line is good enough. But what angle? It can be characterized with the angle between polarizing voltage and middle section of the. I have this normal. Actually, in terminology of this polarized directed relays, this is called vector of maximum sensitivity. And this angle, maximal utigum, angle of maximum sensitivity, no utigum, sensitivity. This is line of max sensitivity. And what will be angle? If I take even distance, this angle should be something like minus 45 degrees. Minus 45 degrees. Actually, this straight line works. Nowadays, to make a bit more reliable, you can have still minus 45 degrees, but this opening somewhere between 120 and 150 degrees symmetric. It's a bit more reliable. Anyway, 180 works, but line of maximum sensitivity for 90 degrees relay should be minus 45. From voltage to current. Watch it closely. In some cultures, angle is measured from voltage to current, and another from current to voltage. Here, in our tradition, angle is from voltage to current. Minus 45 means what current is ahead of voltage. Fine. Yeah, I promised a table. 1 second, I will write a table of 3 different polarization schemes. It may be called polarization schemes or power flow direction connection. 1 second, not to make a mistake.
I buy certificate Professor, yeah, I have one doubt. In the network, how we can choose the relay? Because directional relay, overcurrent relay, ground fault relay. We have 3 types of relays.
More.
More of relay.
More.
But how we can choose the correct point of relay? Because the ground fault relay also measuring the reverse directional current.
At this moment, we speak on overcurrent.
Overcurrent.
Don't worry. I will tackle Earth fault also.
Overcurrent relay and the directional relay. 2 types of relay.
Yeah.
Because if the fault means
Wait, I will draw. Don't worry, I will draw with protection. Don't worry, everything will appear. First connection. I will draw it here. All this logic, don't worry. So, A phase current, B phase current, C phase current. For so-called 30 degrees connection. Another alternatives, it will be AC, BA, and CB. Our 90 degrees. It will be BC, CA, and AB. 90 degrees. Not aesthetic. Two schematics with phase current and line voltage. Most popular European is this 90-degree version, but this also can be used. Very small difference. Old time analysis showed what in 30 degrees it is a bit high possibility of fail stripping of directional relay in case fault is on the client side after transformer delta star. But there is no very much difference. Only what fostered 90 degrees connection of voltage transformers.
30 degrees is a fault.
But that 90 degrees is appears to be a bit more reliable. Difference is small. Also, there is a third can be exist schematic with phase difference, so-called 60 degrees. Known as 60 degree schematic. It will have currents as a difference. It's intended to work from differential current. And I see it had two coil this direction relay was with two current coils, and voltages AC, BA, and CB. more sensible, but write it with the capital 60 degrees schematic becomes unreliable if you have delta star transformers. If you have in your system transformers delta star, this schematic will become absolutely unreliable. It's not sensitive to fault. There will always be a fault when this system, it will not operate. So it's not, in our system, it's not usable. Okay, now what about structure of protection? Question, what type of relays or in reality functions of terminal I need to use? Structure of protection at the first glance. What I need? First, I will need an overcurrent relays. Current bigger, current bigger, current bigger. Operation of any A phase, B phase, and C phase currents. Second, I will need a set of what? What I'm doing. Power flow relays. I will need, for simplified, I need two functions. Actually, I can deal with two, but better three. For them, I will have, again, A phase current, B phase current, and C phase current. And what? A, B, C voltages. BC voltages for 90 degrees. What was next? What was in table? I need 90 degrees, so it will be CA. CA. BC. CA. Oh. BC. CA. And for this one, AB. Should be AB. Everything fine. A, B. Yeah. Connected. Now. And you know I'm making a mistake. Where is my mistake? Because I need to do it this way. Oh, I'm making a mistake. And you will go here I can create a terminal. Hey, why? Why? Delta T and yeah, here is a simple single stage directed protection. Single stage. In case you need two stage, you will have, for example, and this should go maybe in different color, approximately here and oh, this is two-stage schematics. With first I need to save, that's why this I need a 0 time for it. Since I need a 0 time for it, I will have or here trip of any of these and signal here. Yeah, this to allow it to operate instantly. For instant operation, yeah, now it operates instantly. Yeah, this is two-stage. Now, you see, set of relays. 1, 2, 3 sensitive overcurrent relays. At last pair, high current overcurrent relays. 3 power direction relays. And 1 time. Case your protection. Nice. Yeah. But there is one problem. Actually, it can have also third stage with time-dependent characteristic. Time-dependent relays can be directed. No problem. Problem is in the current. This is big current, and here is no connection, but no. Here will be a phase current. Oh, nice schematic. It's a small protection. Only two direct zones. Yeah, finalized. A phase current, B phase current, and C phase current. Boom. Where the dock is digging? Where the problem is? Can I erase? You got the zen of this. where the problem is. Any real relay has a limited sensitivity. Angle of maximum sensitivity here is U-trip minimum. Minimal voltage where relay is capable to operate. Minimal voltage sufficient for relay to calculate the angle. Here will be some big marks. I'm interested in this. It's a minimal trip voltage for my power direction relay. Why it's important? Why this characteristic is important? One moment. Let's say I have line, my protection, and free phase fault. Fault current will be something like this. But what about remaining voltage? Voltage at relay point. This is voltage available to my relay. Draw a line. Minimal trip voltage, and what you will get, this is called blind zone. It's a part of line where, in case of three-phase fault, relay is not capable to detect direction. So this will be not protected. And what is the, let's say, most possible scenario for three-phase fault? Your personal walked on line, put an earthing, and forgot about it. Switch on fault, switch on three-phase fault. Switch on fault is better than the dead lineman. But anyway, it's a problem for protection. Switch on fault is a possible scenario. It's a scenario possible when lineman walked and left earthing. I don't know, portable or just this earthing knife. But line was earthing. After dispatch called, you finished? Yeah, we finished. They finished, yeah, they go. They decided to take a lunch. Asset remain. Dispatch sends command switch on, and there should be a log. But if it's if everything is organized well, all this portable earthing, you saw this three tails cat, one long and three short, three for phase and one for earth. They all should be stored with logs, and responsible person who has a right to operate power switch should solve them. 1, 2, 3, oh, one missing, where is one? But if it's a situation what contractor came with their own operator, the dispatch sits in his nice office and contractor works. He calls contractor, you did everything. They are actually two different companies with two different management. Everything will remain. Dispatch sends a switch on command and we got switch on fault. Where's everything? Here, on a 0 kilometer. So it's the most possible scenario. And we have no protection. What to do? At first, modern directed relays has a memory. In case of three-phase fault, they can take from memory direction of voltage before fault. But it will not help him. Because before we had 0. We have a switch on fault condition. The ideas first, because it's a 0 kilometer, we can use a special protection 1, 2, 3, 4 with very high trip current, protecting only very small part of the line. It will be not directed with low sensitivity, but it will operate instant. It's not a bad idea. Probability of fault here is not so much, but much better solution is older version called speed up, modern version be different. One moment, what means this speed up? In general, what we have, let's say, 1, 2, 3 overcurrent, yeah? Okay, simple, 1, 2, 3 overcurrent. Angle, 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 delta T time. Yeah? Here is a very simple signal flow. What's the idea of speed? You have your power switch, or your circuit breaker. Take normal closed contacts of the circuit breaker and apply to timing relay. Contact of this timing relay this is odd function. Trip of any produces 1 here. Goes to delayed release timer. It's a timer of delayed release. TOF. Timer of delayed release. And here. How will it work? Your switch is disconnected. Here we have 1. This coil energized. At the moment switch connects, coil will be de-energized. But for some 1/2 second approximately, this bypass network will be active. This time, this bypass network will be active for half a second. If inside this half a second, second sensitive zone of protection trips, signal goes to disconnection immediately without any delay. That's why it's speed up. It's for the short period after switch, when switch is disconnected, and for a short period after switch is connected, this will create a short time bypass network. This bypass network for switch on fault scenario. it's an older version. For newer version, so-called non-selective, actually in terminology, there is by speed up before and speed up after. This one before, because signal to reduce operation time, to reduce delay, comes before switch is operated. For case after, signal switch on. So signal to the C, this signal is taken to the time relay. This is speed up after. Here, bypass network is activated by switch disconnected state. In this case, bypass network is activated by command switch on. I don't like this version because it is possible to operate switch directly from the with mechanical buttons. In first case, anyway, this will work. This will operate. For the second one, not. Anyway, you can use both. Okay, what about today? Modern approach, bit more complicated. On the one hand, you don't have direct access to timing function, but that's not all. See where big problem is. If you have only 2 or 3 zone protection, it is easy to select which to speed up. If you have something like 5, which one to activate. That's why more compact scheme is used. It has very large current, width T0, non-directional. Current bigger. It's this one is a backup, very short, so-called, let's say it's 0 stage. This will be, let's say A1, first stage, directional, but with T0. Sorry, it's voltage. Next one, sensitive one. Directional and with delta T. And special one sensitive without function, without delta T, but activated. With delayed action. It is called non-selective OCP, overcurrent protection. Non-selective. Special stage, sensitive enough to protect my line and adjustant. Non-selected overcurrent protection. NSMSR in Latvian, neselektīva maksimāla strāvas aizsardzība. Non-selective overcurrent protection. Activated for time up to 1 second after switch is turn on. actually this stage acts only in switch on fault conditions. Non-selective overcurrent protection. I will need 1 to 3, 1 to 3, 1 to 3. They all three phase. And here terminate. Non-selective overcurrent protection activate. Actually, it activates by switch off signal. Also, command switch on, command to switch on command. This command also may be used to activate non-selective overcurrent protection. So directed overcurrent protection needs at last speed up or non-selective overcurrent protection for backup because it has native blind zone for case switch on fault. Memory will not help. And last for today, I need to give stage for next lecture. Coordination. How coordination is performed. Coordination is done in the way of so-called cross-contact directed. So you will create two independent coordination charts. A, B, C, D. So first, A1, A2, A3, C1, C2, and so on. You coordinate this direction, then you coordinate in opposite direction. Cross-directed coordination. Here is schematic of coordination. First go, how to say, this way, coordinating for current I1. Next, coordinate for current I2. Here's your way of coordination. Selectivity chart. You draw separate for each direction. So you will have two selectivity charts. One for each direction. Can time dependent zone be directed? Yes, it can be directed or polarized. Some scholars use not term directed but polarized. Polarizing signal for the relay. It's our voltage. And please, don't make me go to jail. Do not use current difference scheme on distribution network where delta star transformers are used. If you do so, I will kill you and will need to go to jail. Okay, I think it's enough for today. Well, simply I don't have more time. Maybe someone have questions? And online, maybe online someone have a question. I have viewers online. Chart, what we have. Ooh, yeah. Time is running. Okay, I see no questions, so I can end today. Next time I will tackle earth field protections. This one is face-to-face for distribution networks. Earth field is quite different. Earth field has its own signal